This topic is Bellman's equations, and that's vital for reinforcement learning, and it's based on the Markov decision process. So how do we define a Markov decision process, or MDP? It's a 5-tuple consisting of a set of states of the environment, a set of actions that are available with the agent, the state transition probability, which is a mapping from current state action to a next state to the probability, which is between 0 and 1. The reward function, which is a mapping from the set of states and the set of actions to a real number. And finally, the discount factor, which lies between 0 and 1. So these 5 parameters, or entities rather, define the MDP. Policy. A policy dictates the actions that the agent would take given any state. So informally first, let's take up a few very common examples in chess. One policy could be keep attacking the opponent's king. Whenever possible, check. Otherwise, another policy would be to keep taking the opponent agent's pieces. Whenever you can kill something, do it. Otherwise, a third policy would be to maintain all your main pieces close to the king, so that's a defensive strategy to play. So these are 3 possible policies when you're playing chess. Driving, one policy would always be to remain in the right lane and to drive 2 mph below the speed limit. Another policy could be more aggressive, to drive above the speed limit and keep overtaking other cars. A robot could have 2 policies. One policy could be to always keep close to the charging stations to replace battery if it runs out of battery. Another policy for the robot would be simply to take the shortest path to the destination without bothering about the charging stations. So these are informally what policy means, examples. So now let's define what a policy is. A policy determines the action A equals pi s from any given state S. So pi is a policy and it's a mapping from the states to the actions. So given any state, if the policy is known, then the policy tells you what action to take. Discounted total reward. So once the policy is known and the initial state is known, policy is pi, the initial state is s. The SARSA sequence is, remember, state, action, reward, then the next time step, state, action. So that's the SARSA sequence. Now it is state, action is automatically determined from the state because the policy is known, and then the reward likewise is just a function of s once the policy is known. So pi s is the action, but we already know what the action will be for the state. So the reward is merely a function of s once the policy is known. And then this is the actual transition, and this action A is, I've written A, but it's pi s. And pi s prime is the next state. So this transition is from s to some other state s prime. And pi s prime is the action from the next state, and r s prime pi s prime is the reward from the next state, and so on. That's the SARSA sequence. The state sequence is s, s prime, s double prime, and so on. And the reward sequence is s pi s, then r s prime pi s prime after 1 time step, and r s double prime pi s double prime after 2 time steps, and so on. So the total discounted reward is R pi S, now this is uppercase R, this is the total discounted reward. That's immediate reward R S pi S plus discount times R S prime pi S prime. That's the reward for the next iteration, and then gamma square times R S prime pi S prime prime, and so on. So this is the discounted total reward, and this can be rewritten in this form, R S pi. Now here the reward is merely a function of the state and the policy. So the policy dictates all actions from any state. So that's equal to Rs pi s plus gamma times uppercase R S prime pi. So this is from the next state S prime, what's the total discounted reward, and we discount that with gamma, and this is the total discounted reward from state S. And this is based on the recursive relationship that we have seen before, which is in the episodic setting given by this expression. Rt equals lowercase r t plus gamma times uppercase R t plus 1, and instead of the time steps t and t plus 1, I assume that we are in the state S, and then we have taken action based on the policy pi s, and the next state is S prime. So we follow two different kinds of notations in the subsequent discussion. Now we must note that this SAS prime is a probabilistic transition. Also note that this A, I have written A, but this is simply pi of S, where pi is the policy. This is probabilistic, this transition, which automatically makes everything in the future, all the quantities, also probabilistic. So there is element of uncertainty associated with everything that's beyond this current time step. So we replace this term Rs pi s, this is the recursive relationship, which is immediate reward plus discounted future total reward with the expected value. So R pi s now is Rs of pi s plus gamma times expected value of future uppercase R. So now we turn our attention to an important concept called the state value. So what's the state value? Informally, it gives you the value of a state. You are in a particular state S. So what's the value of that state? And that, of course, depends entirely on the discounted total reward, and which is given by immediate reward plus discounted expected future rewards. So this is what we have. Rs pi is lowercase rs of pi s, the action, plus discount times the expected future reward, because this S prime, the next state, is unknown, it's probabilistic. The transitions are probabilistic, that's why. Now we can rewrite that explicitly using the transition probabilities. So this is Rs pi equals immediate reward based on policy pi plus gamma times, this is the expression for the expectation of the future total reward. That's probability of transition to state S prime times the reward, total reward from state S prime. And of course this action A is dictated entirely by the policy pi, and this summation is carried out over all possible next states S prime. So the state value is defined in terms of this discounted total reward. The state value, or simply value of a state, S, under a policy pi is the discounted total reward when the state S is the initial state. So you are in state S. The state value, the value of this state S, is simply the discounted total reward, and of course under policy pi. In other words, we have this. So this is the expected future reward, expected total reward rather, under policy pi, and that's equal to the value of the state S under policy pi. So this is the value of the state, V pi S under policy pi, is nothing but the discounted total reward from that state under policy pi. And everything else remains the same. Now, here, once I define the value of the state, this is the expected reward, future reward from state S prime. And so that can be replaced with this, V pi S prime. And so this is an important relationship, which I've written again here. So the value of a state under policy pi is equal to immediate reward from that state under policy pi plus discount times summation of the probability of transition to every state S prime times value of the state S prime. Now, this can be written in vector matrix notation in this manner. So, since we have all these states, we have so many different states, so we can write V pi S as a vector, one entry per state. And the reward, again, is merely a function of state, because once the policy pi is known, you can simply drop this argument. It's determined from the state. So I write this as another vector, R pi, the reward vector, immediate reward vector under policy pi. And this is equal to gamma here. And this is the expected value of the next state, S prime. And since S prime is unknown, so we have this here, factor P pi, which is a matrix of all probabilities, transition probability matrix is what it's called, times V pi again. So V pi is equal to R pi plus gamma times P pi matrix times V pi vector. Whence we can solve it immediately like this. V pi equals 1 minus gamma times the matrix P pi inverse times R pi. This should be lowercase r. Now, why don't we solve it this way? First of all, the number of states is extremely large in some cases. And the computational complexity of using this method, which involves matrix inversion, is order S cube, which is phenomenal when the number of states is very, very high. Now, the state transition probability matrix may be unknown. If you're playing a game of golf and you're trying to find the value of a state, then P pi is something that you normally don't expect to have access to. And the number of states could actually be infinite. That's another reason, in which case we don't have to determine the value of every possible state. Only the main states that are going to be visited. Some of the states are very unlikely to be visited. So we don't have to evaluate the values of those states. Only the ones that are going to be visited on a probabilistic basis. So this is Bellman's equation. This is the scalar form of Bellman's equation, and this is the vector form of Bellman's equation. An example will make it clear. So let's take up a simple example. So I have a set of 4 states here, P, Q, R, and S, and I'll denote the set of states as this block S, and each state will be in uppercase. Block A is the set of actions, and I have 3 possible actions available to the agent, and for simplicity I will assume that given any state, the agent can in fact take any possible action, and the actions will be in lowercase, and let's say the discount factor is 0.8 gamma. So here are the transition probability tables. P, S, A, S prime. A is now the specific action A. Don't confuse it with any action A. It's the specific action A here. And so if I am in state P, then if I take an action A with a probability of 0.9, I will be back in state P, and with probability of 0.1, I will transition from state P to state Q. Likewise, just to take another example, suppose I'm in state S and I decide to take action A, then with the probability of 0.1, I will land up in state P, and with the probability of 0.9, I will remain in state S. So this table here is all the probabilities for action A. Now this is all the set of all probability transition probabilities from S to S prime given action B here. This is B, and this is the current state P, Q, R, S, and the probabilities of the next states P, Q, R, S will be given by these entries here. This table is for action C, all the transition probabilities. And so that completes the state transition probabilities. P, S, A, S prime for any action A, any state S, and any next state S prime. We have this. So remember, in general, the transition probabilities will be 3-dimensional matrices like this because you have 3 arguments: current state, action, and next state. Now the reward will be 2-dimensional as shown here because it's simply a function of state and action. So for every possible state S and for every possible action A here, and this A is a specific instance of this action A. So these are the entries of the table, which are the rewards, the immediate rewards. And let's define a policy. Pi of P is A. So when we are in state P, or rather the agent is in state P, it will take action A. From state Q, the agent will also take action A. From state R, the agent will take action B, and from state S, the agent will take action C. Now, given the policy, so we have the policy here written again, and our goal is to find the values of the states. We have 4 states, P, Q, R, and S, and under this policy pi, this is the policy, it's pre-specified. We have to find the values of these 4 states. And this is, once you have the policy, the Markov decision process reduces to a simple Markov chain, a discrete Markov chain or a discrete Markov model, which you are familiar with, I hope. And what this example we will do is, we will find out the state transition probability matrix and the reward matrix. And you'll see why I have colored this Markov model in this manner. So once again, here are all the tables, the transition probability tables and the reward table, and this is our policy here. Now let's say we are in state P. Under this policy, if we are in state P, the action taken will be A always. So action is A. We have to look at this particular table. So we are in state P here, and we take action A. So we are looking at this table, and so what are the probabilities of moving to or transitioning to states P, Q, R, and S? They are given by these entries here. 0.9, 0.1, 0, and 0. And what's the reward? So under policy pi, the reward for state P is 0. So I have written it down here. This is from state P. The probabilities of transitioning to states P, Q, R, and S are given by these elements shown in red, and the corresponding reward under the same policy pi is 0. Back to the tables and the policy. Now suppose we are in state Q. We still have to take action A. That's what the policy mandates, that when you are in state Q, you have to take action A. So this is when you're in state Q under 3 different actions, but we know that the action is A here, so we have to again look at this table because that corresponds to action A. And what are the transition probabilities? These are the transition probabilities. When you're in state Q under the policy pi, the transition probabilities to states P, Q, R, S are 0, 0.9, 0.1, and 0. And what's the reward? The reward is 0 because under policy pi, you are taking action A. This gives you a reward of 0. So we fill out the next rows of the transition probability matrix and the reward matrix based on the new probabilities that we obtained earlier. Now let's look at when we are in state R. From state R, the policy dictates that we have to take action B. So we look at this table here, which corresponds to action B, and since you're in state R, the transition probabilities are 0.4, 0.6, and the reward is still 0 under the policy pi because the action is B. So 0.4, 0.6, and 0. So these are the new entries that I got for the state transition probability matrix and the reward matrix. Now for the last state S. And when we are in this state S, we have to refer to this table here because this table corresponds to action C, which is what the policy warrants, and the corresponding reward is 10. It's actually, it's this 10 here, not this 10. This 10 is the action C. So this is the final set of the 2 tables that I have. All the values are shown, and Since now all the probabilities reduce to two dimensions, because we have eliminated the action once the policy is given, so it's a two-dimensional matrix, and the reward is a one-dimensional vector here. And these colors are used to define this simple Markov chain here. Of course, I have not shown the rewards in this Markov chain. And now, how do we determine the values of the states P, Q, R, and S? Now, that's very simple. We can use the Bellman's equation to do that. So here is what we get. This is P pi, the state transition probability matrix, and this is R pi, the vector of rewards, and we can use this expression here, V pi S equals R S pi S, which is obtained from this, so plus gamma times summation transition probability. Now this is eliminated, this A is eliminated because we know the action under a policy times V pi S prime. So we get these expressions. We let lowercase p be equal to value of state uppercase P, lowercase q be equal to the value of the uppercase Q state, lowercase r be the value of the state uppercase R, and likewise for the S. And so the values are P, Q, R, and S. The values of the four states are equal to reward, which is 0, 0, 0, and 10, which I just used these values, times gamma of the transition probability. So let's look at the first one. Transition probability is 0.9 back to state P, so 0.9 times P, and transition probability to state Q is 0.1. So 0.1 times value of state Q. This lowercase q and lowercase p here are the values. Likewise, for the remaining, we'll just do one more. So the value of the state Q is equal to the reward for state Q under policy pi, of course, plus gamma times, when you're in state Q, with the probability of 0.9, we go back to state Q, and with the probability of 0.1, we go to state R. And so 0.9 times lowercase q, value of state Q, this is the value, and 0.1, which is the probability, times value of state R, which is lowercase r. Likewise for the remaining two expressions. We'll continue in the next presentation, which shall be the Bellman's equations with state action value.